Yeah. First of all, remote sensing, basically we are talking about the art of being able to get information about something without being in touch with it. And there are several forms of remote sensing that are being used. Some of them being the variation in force distribution, and example being force of gravity, which is being measured using a gravimeter. And then we have the electromagnetic energy distribution, which is the most common form of energy that is being used in remote sensing. And my presentation will be focused around the electromagnetic form of remote sensing. The electromagnetic energy composes of the radio waves, which are the longest waves. We have the infrared, we have the visible spectrum, we have the ultraviolet, we have the X-rays, and the gamma. And most of the electromagnetic energy that we use is from the sun. As the sun propagates its energy to the surface of the earth, is being reacted to by different phenomena, some of them being the atmosphere. Some of the energy is being scattered in the atmosphere. The one which manages to penetrate until it reaches the surface of the earth is also meeting some of the objects on the earth, some of them being trees, water, and many other objects, which absorb some of the energy and reflect some back into the atmosphere. And here I was trying to show how different phenomena react to electromagnetic energy from the sun. In these curves, I was showing how soil reacts to the visible energy. There is high reflectance, so it highly reflects the visible energy all the way up to the shortwave infrared energy. Then when you look at the green vegetation, it absorbs some of energy within the blue and red zones, and then it reflects highly in the green region. That's why we see green vegetation, and also reflects a lot of energy in the near infrared before it absorbs some in the short infrared region. And then water, clear water, it reflects highly within the visible region, and then it absorbs almost everything thereafter the visible region, being in the near infrared and the shortwave infrared. And the water that is not clear, the contaminated water, the water with phytoplankton, you see it doesn't reflect a lot of energy as clear water. So there are variations in how they react. And this brings my discussion also to the fact that different objects react to different energy depending on their composition or their makeup. And I'll show you in a bit variations in plant reflectance of energy or reaction to energy. As I've already alluded, the green vegetation and the visible bands, it reflects highly in the green, and then it has high absorbance because of the chlorophyll in the red region. But dry plants or plant with stress, it reflects highly in this area, in the red region. And most studies that uses remote sensing to study plants, they use these regions. It's called the red edge region. That is between the red bands and the infrared. And like I said, we have different types of sensors, being the passive sensors, which uses the passive sensing method. And these ones, they use the energy that is being emitted by a different source to study the behavior of objects or various objects to that energy. Then we have the active sensors. The active sensors, they produce their own energy, and they also detect how different phenomena on Earth reacted to the energy they are producing. And with the passive sensors, normally when we talk about these ones, we talk about the sensors that react to energy between the visible bands and the near infrared, but also we have those that react to the emission of energy on Earth, and those are that reacts to the heat that is being released from that is being released by different objects on Earth. For example, as the sun is heating, or different objects are releasing their own energy, like human body. And this reaction by different objects to the electromagnetic energy is being recorded. Traditionally, it was being recorded using photographs, which were detecting these reactions and recording them on film. Now we have the digital image recording, which record the electronic signals that corresponds to various energy that corresponds to energy variations in the scene, or in the scene. And these sensors are carried by different platforms. As I will elaborate going on, we have the sensors that are called the ground-based, that are held by ground-based platforms. These are your cameras that you'll be holding with your hands, or those that are held on raised platforms. Like the example I'm showing here is a camera being mounted on top of a vehicle for Google Street Mapping. And then we have what are called the airborne platforms. The airborne platforms, we have the aeroplanes, we have the drones, and we have the hot air balloons. And then there are the space sensors, or the space platforms. The space platforms are those that are like satellites, which are orbiting in space. And remote sensing also is affected by what we call the resolutions. There are 5 most common resolutions, one being spatial resolution. And when you talk about the spatial resolution, basically we talk about how big or small a sensor can see, or the object that can be detected by the sensor. We have the temporal resolution. Temporal resolution, we talk about the time a sensor takes to image a certain portion. That is the revisit time. If it, for example, if it passes Botswana today at 10, and then it comes tomorrow at 10, we say the temporal resolution is 1 day. So the time it takes between the 2 intervals to image an area. Then we have the spectral resolution. Spectral resolution, in simple terms, we talk about the amount of energy, or the variation of energy bands that can be picked by that sensor. Then we have the radiometric resolution. The radiometric resolution, we talk about the smallest variations that a sensor can pick in terms of the data values. And I will explain this later. And then we have the view angle, the angle at which our sensor is when it captures the images. Now, going back to spatial resolution, as I said, the spatial resolution for a human being, because our eyes are also doing remote sensing. We study objects mostly without being in contact with them. So basically our eyes are also sensors, and the smallest thing that we can see on average is 50 micrometers big. And now when you talk about this, you'll find that the image is presented in pixels, or they're called picture elements. The small boxes, if you zoom into images in your cameras, you will see the small boxes. Those are called the pixels or picture elements. And here, as I was saying, we have the high to very high resolution sensors. Those are that can pick the objects that are as small as 30 centimeters and up to 5 meters. The range of the smallest objects that can be picked ranges between 30 centimeters and 5 meters. And then we have the medium resolution sensors. The medium resolution sensors are the sensors that can pick the objects. The smallest object it can pick should be 10 meters or more. And in most cases, the resolutions for these ones are between 10 and 30 centimeters. And the lower resolution sensors are those that can pick objects which are 60 meters or big. And then, like I said, there is what is called spectral resolution. For a human eye, I will say the spectral resolution for a human eye is the visible, is in the visible region, what a human eye can see. But with our sensors for remote sensing, you find that different sensors have different spectral resolutions. There are sensors that can pick only objects or light or energy reflectance within the visible and near infrared region. And I gave an example of WorldView 2 here. And then we have those sensors like Landsat 8, which picks the variations or the reflectances within the visible range, the near infrared, and even in the shortwave infrared regions. And here I was trying to show the various resolutions for human beings, for bee, and for butterfly. And these resolutions, I show them in simulation that a rose or a flower that you see in red, for a bee, it appears in different color. And for a butterfly, it even appears in much more different color, because we have different spectral resolutions, or you see different light reflectances. I think I talked about the temporal resolution is the revisit period. And for different satellites, you find that or different sensors, you find that the revisit period differs. In most cases, you find that sensors with lower resolution takes a lot of time to pass, or before it can pass over the same place again. And those with very high resolution take less days, so that before passing over the same area again. And why is this temporal resolution important? Temporal resolution is important in remote sensing because we use it for change analysis or change detection. Since this sensor passed this area, what has changed or what has happened? And like I said, with radiometric resolution, it is important because it helps to pick slight variations. And by doing so, it increases your ability to see even small changes in your study area or in what you are studying. And the range for radiometric resolution is expressed in powers of 2. We have 1 bit which contains 2 values. It's in binary, it's either 0 or 1. And then we have 8-bit resolution. The images with 8-bit resolutions contain about 256 values, which ranges from 0 to 255. So it means that it can give smaller details of changes within the pixels. Remember I said the data is recorded in picture elements. Those are the spatial resolutions in most cases. And then we have the 16-bit resolution, which is of much higher resolution because it can record up to 65,335 changes or variations. And all these are recorded as values within the pixels, and they are called the digital numbers or brightness value. And because I've been talking about remote sensing as detecting variations in those spectral resolutions or in light reflectances, how is it benefiting us in archaeology? You find that in archaeology, our sites have various chemical and physical compositions because of the human activities that occur within them. In some areas, we find that there was a wall that has been constructed, and you know where a wall has been constructed and is being covered by soil or is not covered, there will be less moisture within the wall. And in some cases, we find that people have dug a ditch, and you know where a ditch is being dug, there's a bit of accumulation of organic deposits and fine silts or fine soils. Most of these deposits, we find that they are very rich in nutrition. And if the rain comes, we'll find that the ditch, because of those loose particles and rich organic content, it retains much higher moisture, and also because it already has high nutrition value from the organic deposits, the vegetation that grows on the ditch, it grows much healthier than the vegetation from the surrounding. And when you look on top of the wall, you'll find that there is a difference. The vegetation, because of the starvation of moisture, that is because of low moisture on top of walls, and maybe less nutrition, the vegetation tends to be a bit stunted when compared to the vegetation in the surrounding. And because of the variations in their reactance to the light that is being emitted to them, we find that they reflect differently. They reflect that light, or they react to it differently. And those variations, those are the ones that we use to capture areas of various activity on the archaeological site. And that will be clearer when the case studies are being discussed. And with this, I end my presentation.
Many thanks for that wonderful overview of the remote sensing in archaeology. It's very much appreciated. At this point, I would just, and she's going to talk to us about leveraging LiDAR for landscape archaeological research, representation and management. Rachel, could we share your screen now, please? And we will now start recording again.
Yeah, I think Dr. Tabang probably has to stop sharing for me to take over.
Thank you. Perfect.
Thank you. Let's just see. So thank you so much for inviting me to talk to you all today about archaeological applications of LiDAR, one of my favorite topics. So for those of you who don't know very much about LiDAR, I thought I'd give a very brief introduction. So LiDAR is an active remote sensing method. It is used basically to create really detailed digital models of the shape of the surface of the Earth and objects on it. So the way that this works is that you put a laser scanner, which is basically a machine that sends out a laser impulse, which then bounces back off the surface of any object it encounters, and that signal is recorded when it bounces back. So you put one of these laser scanners normally into an aircraft. So there are lots of different types of LiDAR, but today we're talking about the aircraft mounted type. And you fly this scanner across the surface of the Earth, which is what we see here in the diagram, and you collect lots and lots of measurements of the surface of the Earth and objects on it. So trees, houses, small sheep, whatever is hanging about. And you then take this collection of measurements and you use it to create your digital terrain model. So this is just another view of the same explanation that I've given you. You fly your aircraft across the surface of the Earth, taking all of these different distance measurements, and you essentially end up with a whole collection of XYZ coordinates. So location plus elevation, and this is normally then visualized in something that we'll call a point cloud, which is what you hopefully see down here. And this point cloud is a really interesting remote sensing data source for archaeologists, because what we can do with it basically is we can manipulate it digitally. So through a process that we call classification, where we assign different points to different types, we are essentially able to separate the points from the surface of the Earth. So from the ground, from the points from the returns that have come back from vegetation, sheep, houses, other things that are hanging about on the surface of the Earth. And what this then allows us to do, which is really interesting archaeologically, is to essentially get rid of all of the buildings, get rid of the sheep, get rid of the trees, and to see a model of just the surface of the terrain, just the topography, which we can then manipulate visually in different ways, which I'm going to talk about in a moment. And so for archaeological purposes, what we're really interested in with LiDAR are these very, very detailed versions of the model of the surface of the Earth. So ones where we have, normally we'll say kind of 16 points per square meter on the ground is about what you want for archaeological work. So this is a very high-res spatial resolution data set, if you think of the spectrum of resolutions that Dr. Tabang was talking about earlier. Now, one of the nice things about LiDAR for archaeological research is that we can digitally manipulate these terrain models that we obtain. And there are lots of methods for doing this. I'm just going to show a couple here this morning. So one of the key things we do is we simply manipulate the way that light, an artificial light source, is cast across the surface of our digital model of the Earth. So here you see a model of a set of fields with what are referred to as ridge and furrows. This is kind of evidence of past agriculture. And we have the light kind of coming from the top left in this version, so 315 on a circle from 0 to 360, and 45, so 45 degrees from the surface of the Earth as an angle. And you can then say, okay, well, I want to see the light from a different angle. So you can move the light digitally to a different position, so say to 45 degrees on the clock, and hopefully you were all able to see that the features that are visible, the archaeological features we're interested that are visible on the surface of our digital terrain model, change as we manipulate the location of the light source. So as a source of remote sensing data, this is really interesting to us because we can pull out detail by manipulating the digital terrain model. So that is just one way that we visualize a digital terrain model. Another way that we might visualize it, so that first one is called a hillshade. This is called sky view factor, which essentially does kind of what it says on the tin, in that it is a calculation of, if you were standing at any given point on our digital terrain model, how much of the sky you could see. So if you're on the top of the hill, you can see a lot of the sky, and you're going to get very kind of bright values. It's kind of visualized as a bright point on your digital terrain model. And if you're in the bottom of a well, you're not going to see very much of the sky, and everything is going to be very dark. And so this model allows us essentially to, once again, visually pull out lots of detail of what we can see archaeologically in the digital terrain model. So hopefully you're seeing lots of squiggly lines, lots of features that represent, in this case, the remains of a complex of buildings. So this digital terrain model is a really rich data source. Now, we have literally dozens and dozens of ways that we can visualize the terrain model. And what we then do archaeologically is we go through and we interpret what we think we can see in the model. So it's a visual interpretation practice where we say, okay, you know, I think that that feature looks like the upstanding remains of the wall of a building. I think that that feature looks like the remains of a field system. And we then in GIS normally are going through and drawing the shape, the extent of these features. And this is really a method of working with remote sensing data that has deep roots in certainly the UK and European tradition in archaeology of working with remote sensing, in that we interpret our topographic evidence on the basis of both seeing it from above, so from aerial photographs traditionally, and from work on the ground. And there's a long, very rich tradition I won't go into today of how we draw and depict these features. And what's really interesting with LiDAR at this point is that we are essentially taking this set of practices and we are translating them to work with digital data. So we're taking everything that we've done for more than 100 years in the field, and we are learning to do that same kind of topographic interpretation with our digital terrain models from LiDAR. And so there are lots of interesting implications of this. Now, one of the main archaeological impacts that I want to run through with you is its impact on our ability to survey in forests. Now, I glossed over this previously, but that bit where we can classify the point cloud and separate and remove the points from the trees basically means that we can see in immense detail the shape of the surface of the earth preserved under forest. And this is huge for archaeology because most other remote sensing data sources do not allow us to see through the tree canopy. So this is why archaeologists are very excited about LiDAR. We really enjoy it. And as I probably do not have to tell you, much of the surface of the earth is in fact covered in forest. So this is a really important remote sensing data source. I will note that nice chunk in the center of Africa where there are not a few forests. And LiDAR also allows us to see the same kinds of topographic features in areas with shrubs and grasses, which again are less amenable to a lot of other remote sensing methods. So one of the really big things that has happened with archaeological LiDAR is it has really changed the position, changed our ability to comment on what is going on and to get involved in debates on the impacts of deforestation, afforestation, and forest management, which, as you all know, are really entangled with contemporary debates on everything from mitigating climate change to the changes in agricultural strategies and where cultivated areas are and how public perceives the forest. So this is all really quite important. So this is a remote sensing method that I would say over the past 10 years has really changed the public perception of today's forest and is the key method for archaeologically investigating the cultural heritage of forests, understanding the length and character of different impacts on land uses, and really promoting forests as being really active economic and social landscapes. So this is an archaeologically important remote sensing data source. So what kinds of things do we see with it? All sorts. We see everything from boundaries that represent old field systems, which are these linear features you see here, to clearance cairns, which are these little bumps. And then these features that kind of are circular and have kind of a dark bit on one side and a light bit on another side are charcoal burning platforms on a hill slope. And these are all things that we have kind of learned to recognize archaeologically in the data. So we end up being able to build up really multi-phase topographic palimpsests. So features that we recognize as belonging to different periods that are aggregated under the forest cover. And this, again, archaeologically is really interesting because it's giving us insight into changing land use, different activities in the same area over time through this remote sensing data source. And so these are examples from the forest Chailloux, which is in Central Eastern France, where I've worked in my own projects. And what these aggregations of features really let us get at are very locally specific pictures of things like patterns of afforestation and deforestation. So what you have here is a series of fields. You can see the field boundaries. You can see all of those little bumps. Those are all clearance cairns. So you see very clear evidence for past agricultural land use in an area that is now forested. So you can see through this remote sensing data set us building up a picture of what is going on in terms of long-term land use change in this area. And these features are really quite difficult to see and recognize on the ground as you're walking around. So I've kind of drawn over one of them there. So this is really an important thing for us, because even if we were able to go on the ground, we wouldn't be able to necessarily see very clearly all of these features and how they relate to one another. So archaeologically, this is very important for us, and we can start to pick out, using this remote sensing data, fairly direct relationships between features that represent these different activities, which will sometimes physically intersect, physically overlay one another. And one of the things that has really emerged from all of this is just the huge extent of evidence for long-term forest economies and intensive phases of active forest management. So you see here, all of these green dots are charcoal burning platforms that were located in one area of the forest Chailloux. The little purple triangles are then lime kilns, which are probably also exploiting the woodland resource. So the number of sites archaeologically that are known in forests have absolutely exploded in the years since LiDAR came on the scene. And this then allows us to really target our survey work on the ground and investigate past forest management through things like strategic sampling. So this also allows us to compare different regional trajectories. So we can take what we're seeing in the forest in Chailloux and compare it with the trajectory of land use patterns in Châtillonnais. So with our colleagues' work, which is also revealing huge complex field systems with evidence of occupation 2,000 years ago in an area that is now heavily forested. So I've been emphasizing the forest impact, but just to say, to remind us as well, that this also lets us see what is happening in unforested areas. This is a nice example from Arran, from an upland area under kind of rough grazing and heather, where you are seeing, again, preserved evidence. This is what we see down here of past pastoral activity, so keeping of animals, that is no longer what is done in this landscape, but that evidence is preserved and is visible in the LiDAR data. So just to wrap up, what are the implications for some of this now as we are developing research and management strategies using this remote sensing data source? One key thing is that I think it's really pushed us towards mapping activity and land use areas rather than features and sites, and I think that's really where archaeological remote sensing with this data source has gone. One thing that I know you're going to be engaging with in this project is getting ourselves on a really landscape footing. So scaling up and employing machine learning methods, which are increasingly used in remote sensing broadly writ, but there's a lot of action around this looking at archaeological LiDAR. There's an excellent project run by my colleague, Dave Cowley at Historic Environment Scotland, who's been leading research employing automation and machine learning on Arran using the LiDAR data there, and really asking what happens when we can't look at everything and what happens when we change our focus from looking at individual sites to whole landscapes, and we're really scaling up and looking at larger amounts of data, which again, I know is something that this project and this research community are going to be engaging with. And this is absolutely critical. And again, my colleagues at Historic Environment Scotland have done some quantification of how long it takes on the ground to work to cover and conduct archaeological surveys on some of these areas. So, you know, you can spend literally, as you see on the slide here, hundreds of days, tens of days to hundreds of days trying to do this survey work. And so this is kind of okay if you are in a sites and monuments management framework, but it's not really okay if you're trying to look at the whole landscape and look at landscape change. You really need to be able to scale up and go faster. And so that is where these studies on machine learning and their use to let us investigate patterns are really coming in. So I'm aware of time, so I'm not going to go into any more detail on that, except to say that this is really the thing that is changing our survey practices today and what we're really going to be engaging with. So I will wrap it up there and leave time for a few questions.
Melin from the University of Newcastle to speak. She will be talking about remote sensing based change detection of archaeological sites in the MENA region. Louise, welcome.
Thanks. I'll just try and share my screen. There it is. Can you see that? I've got it on the other screen, so apologies if I look like I'm looking out of the window. I'm not, I'm looking at my screen. Can everyone see that okay?
It's not in presentation mode.
Okay, so
that's it. We can see it.
Okay, great. So maybe it was a bit slow. My internet's been a bit slow today. So thank you very much for that introduction, and really thanks for inviting me to this workshop. It's a really interesting event and in a way quite daunting, but also amazing to see so many people in the audience interested in remote sensing and archaeology. So I'm currently a research fellow at Newcastle University, but that's quite a recent thing. Until this summer, I was a postdoc in Leicester University working for the AMENA project. And that's another one of these ARCADIA funded projects. In fact, I think AMENA was probably one of the first of these sort of heritage database projects. I'm going to talk mostly about a methodology for sort of change detection of sort of things, human activities and other things that are happening around archaeological sites, with sort of some case studies drawn from the AMENA project. And that's work that was done while I was working for AMENA, but will sort of hopefully continue. So I'm going to talk about a range of data sets that sort of fed into this. So of course we've got a high resolution modern imagery. So the sort of concepts of this are wonderfully described in the first presentation this morning, so I don't need to go too much into that. But we're sort of doing image interpretation from the high resolution imagery. The lower resolution imagery, the multi-spectral imagery, is what we're really using for our change detection. Of course, we're bringing in historical imagery like corona as well. I think there's going to be a presentation on that later. And we're bringing in, of course, fieldwork data, sort of archive, survey and excavation data. And we're using this huge database of archaeological sites to apply some of these remote sensing methods too. So the sites are coming from the AMENA database. This is an ArcGIS database, so I think similar to the other ARCADIA funded projects. I think there's over 170,000 sites there, but it's always increasing. So there's a team of expert image interpreters working for the project, and also many trainees and partners who've been trained in using the database and in AMENA's methodologies of using image interpretation and remote sensing. And this is sort of through a program of training courses. As you can see, it covers quite a large area, North Africa and the Middle East. Probably this map at the top is a bit out of date now, and I need to update it for the sort of areas, the blue squares are the areas where mapping has been undertaken, but I suspect that's ever increasing, a bit like this. It's easy to access online and see which areas have been mapped. So in terms of the sort of remote sensing data sets used, we are using the multi-spectral imagery and the free imagery like Sentinel and Landsat, but we're mainly using that for the automated change detection, for looking at how the landscape has changed over time, rather than for the sort of recording of sites themselves. So we're relying on those multi-spectral properties of how light's reflected from the Earth's surface to recognize particular materials, sort of mostly human activity and natural processes, which might impact on the survival of those sites. We're also using PlanetScope imagery sometimes, which there's a sort of limited free availability of, which is slightly higher resolution of around sort of 3.5 meters. Because it's mostly collected daily, it's quite useful for looking at sort of changes that are happening rapidly. In terms of the sort of methodology, it sort of starts with high resolution satellite imagery and looking for known features we can recognize because the interpreters and all the partners are sort of very familiar with those landscapes to know the sorts of sites that might be visible. And just to sort of illustrate how important it is to understand the sensor characteristics and environmental characteristics. I mean, these are 4 images all show the same site, but taken at different times, some probably different sensors, and you can see it's only really clear in one of those images. And this sort of leads into sort of glossaries that AMENA has of sites and descriptions of what they can look like. So this is another example of a water management feature. My new project is based on water management, so I like to get in a water management feature there. But of course, the MENA is recording them as well. So you can see this fog is very distinctive from space, and also has a distinctive appearance on the ground. So it's about knowing what these features look like so that they can be recorded in a standardized way, and then analysis in the entire database. We can bring up all the fog rows or canats in the database and compare them. And we also use and train a sort of standardized methodology to try and make sure we're thinking about why we're making these interpretations using these glossaries, to understand what what's a modern feature or even just a natural feature. I mean, quite a distinctive site there, clearly an archaeological feature, but modern features and so on around it. So one of the main things I want to talk about today is this sort of change monitoring workflow, which we've been working on. And this is using Google Earth Engine, which is a sort of a platform, a programming interface provided by Google. It's free, you can sign up to it, get an account, and it gives access to sort of free imagery such as Sentinel and Landsat. You can import your own other imagery and data as well. We've got the MAEASaM imported into it. And it also uses high performance computing power, so you just have to have an internet connection to use it. So we're finding this a really good way of sort of disseminating our methodology and making it possible to do some sort of broad change detections. With so many sites in the database and most archaeologists working across large areas, it's very hard to regularly monitor each site on the ground, but this provides a way of finding out which are the sites that are most at risk. So it works by creating composite images of Sentinel-2, so quite simple, using the level 2 imagery, so it's been corrected, atmospheric corrections have been applied, it's calibrated, creating 2 composite images, searching for all the available Sentinel imagery that meets user-defined filters. So the user might give particular dates, say they don't want too much cloud, they just want to look at a particular area. So it might find 1,000 images that meet those criteria, and then it will just take a particular pixel, in this case a median pixel value, across that big stack of images. That would take weeks probably if you were to do that on a normal computer, just downloading Sentinel images or whatever. So this provides a quick and easy way of doing this. It then uses a very sort of simple and established method of change detection, especially for sort of medium resolution data like Sentinel, where it just computes sort of change magnitude between each composite across all the bands. And it sort of creates a change layer, which we also threshold, but the value is appended to a sort of buffered area around each site, where we want to know whether the change is occurring, so we want to know if those are sites that are at risk. And the sort of next stage of this, which are currently underway, are sort of accounting for vegetation and seasonality, but also attempting to classify accurately the types of change we can use, unsupervised methods or such as K-means, or supervised methods such as random forest, where we have to create a bit of a training set to try and understand what the types of change are, to get an idea of what's sort of threatening archaeology most really in any one location. So just an example of it. So this is what the change layer can look like. You can see the brighter pixels where there's been change. So for example, this area here, which is being highlighted as being changed, you can see in an earlier image, we have these nice, very visible warehouses. In the later images, these have been polished. So it's picking up sort of changes like this, any sort of change. It could be demolition, it could be agricultural expansion or loss. It could be rubbish dumping, anything really. It's picking up changes, and it's not really sort of telling us what those are. And we end up with something like this, sort of a list of sites that have been changed, playing around with some sort of attempts to classify it as well. And the user can define the size of the buffer. You might want to look in a sort of 300-meter area around the site, because if it's starting to get close to the site, the changes, you might understand that that site is then at risk and it needs to be checked up on. And this is appended to a simple list, a CSV list, which is easily downloaded by users. You don't have to have amazing internet to just download the CSV. So to properly disseminate this, Amina has been doing a lot of training courses. I think there's probably been many more than 22 workshops now. In fact, there's been some workshops ongoing in the last few months online, training many heritage professionals in North Africa and the Middle East, and training in database recording, but also remote sensing, GIS, and increasingly in change detection. But I should say this is completely focused on sort of open source data and software using Google Earth Engine, QGIS, or Arch's database, to really make this methodology as widely available as possible. We have some nice photos of training and progress here in Tunisia. I think that was a year or two ago. Seems like a long time ago now with the pandemic, that it was actually possible to be here in person. So I'm just going to show you two case studies now of the results of some of the change detection that we've been working on. So one of these is a Jufra area in Libya. So you can see from this time lapse how it's increased since the 80s, especially in sort of agricultural areas and some urban areas as well. And this has been happening very quickly, and it really threatens archaeological sites. You see that there. And we have a range of archaeological sites in these oases, medieval features, but also earlier features, settlements, fogaras, cemeteries, all important sites, and many sites in the area. So too many to sort of regularly visit to detect change. So we need to use some sort of automated method to do so. So these are the results of the initial change detection work done in the Jufra area. So we got a pretty good accuracy overall, and this was partly because we didn't get false positives. However, we did get, there were a few missed sites and some underestimated sites as well, I should say. So the algorithm is reasonably accurate, it's not perfect, partly because it's not using the highest resolution imagery. There are some other reasons as well, a slight offset in the accuracy of the rectification of the imagery, for example, and some sites being very small and not easily detectable. So here's an example of a detected but underestimated change. So you can see here we have a nice fogra, sort of underground water management tunnel here. But you can see in the more recent imagery, it's been covered with planting holes for new fields for trees. You see that was detected by the algorithm, but underestimated. So perhaps we need to work on slightly increasing how it estimates that. But the trade-off is we might get more false positives than false positives if we do that. And here's another example in Jufra of a fogara of a slightly different time period, but it's getting built over, it's being picked up in the change layer. And these are features disappearing very quickly, but potentially some very early examples in this region of fogara irrigation. Now, this is an image from 2012, a high resolution one. You can see the blue lines here, lots of fogaras, associated field systems and little structures, with the new fields starting to be laid out, but not being yet cultivated. And some close-ups here. So it's really a last chance to record these. We need to try and record them before they're lost. And the change detection offers a way to identify the features that are most at risk of being lost. However, we're working with our partner in the region, Dr. Lamin Abdelati, and he's been recording some of these features on the ground as well as using our remote sensing techniques. He's attended some of our training courses. And here's some nice examples of some of the fogaras he's visited and photographed and investigated. In this one, he found some palm fronds in the bottom of the shaft, so he's suggesting this could have been used to cover the top of the fogara shaft. So we're continuing to work on that project. But we're also detecting other changes in the area. So natural changes that we sometimes forget about. For example, on this medieval settlement site here, we've got an area of runoff was detected, but also rubbish dumping. We've got the problem here with the road is almost slightly trapping moisture and stuff here on the edge of the site. This area of rubbish dumping is appearing. And you can see here in the Google Earth imagery that water collecting there along the road, sort of dammed by the road. And that's another problem which is damaging archaeological sites, and rubbish dumping does cause damage, partly just through the presence of the rubbish themselves, but then sometimes the rubbish will be burnt or bulldozed away, so it does cause damage to sites. In some cases, changes were missed, and this may have been because the field was just planted, it was very faint, the field holes are not very large, so it wasn't detected, although when they start planting the trees, it gets a lot more detectable, but this is perhaps something to work on. For example, if we use the PlanetScope imagery, it's actually quite visible here. So perhaps for targeted areas, for small areas, we can use the limited free availability of the PlanetScope imagery to detect those changes. But overall in this area, for example, if we look at the Landsat imagery, we can send it back to the 80s, we can see a very large increase in the size of the oasis. And if we look at the graph here, we can see since the conflict in 2011, it's really increased, partly due to sort of breakdown in planning regulations and people needing to dig their own wells in order to cultivate enough crops. And this directly threatens the archaeological sites. And this is easily detectable in our algorithm. We're finding it most increasingly, most of the sites in the area have been damaged, and most of them, in that case, is by agricultural activity. And we sort of start to see this pattern across Libya again. Probably this image I'm using is a bit out of date, we've got more recorded now. and we're seeing sort of agricultural expansion really affecting the survival of archaeological sites. So my other case study is the Asthma area in Egypt, where EMENA is collaborating with the ACAP project. So we can see another time lapse here. Here it's just a little about urban expansion, the West Bank here. You can start to see the development of something called New Aswan, which is a planned new town. And there's lots of archaeological sites in this area. As you can see, we've been detecting ones which have been changed and looking at the accuracy of that, and we just on that as well to validate. This is a bit different. This is sort of planned construction. We know it's happening, so that it's slightly different from the Jufra example. The ACAP project is directed by Dr. Maria Gatto, and they're recording sites of different types and periods, as Amina does as well. But many of these sites, for example, lithic scatters, are the kind of sites that we can't identify in high resolution imagery. We can't see that on the surface so easily. But we know it's there, it's been recorded by fieldwork, so we can still use the change detection to look for modern changes which might be impacting on the survival of that site. And training is underway here as well, slightly lower accuracy, and we did have more false positives in this area, some of which is caused by sand moving around or by shadow. So those are perhaps a shadow is something we can mitigate a bit in the algorithm. And here's a nice example. There's some lithic scatters and rock art down here, picked up by the algorithm. There's been some change, and this is part of the construction of New Aswan in the background. The sort of track was bulldozed. And we can see since 2018 the sort of development of that work. So it really is the last chance to record these sites, which in fact ACAP is working on. And but of course we have that planned work. We also have less planned work, which is a lot harder to sort of predict. So this is where change detection really comes in. So we can pick up on small changes around the area, the large area that we might not have thought to check up on in person. And we can see this modern cemetery here is expanding and starting to impact on an ancient cemetery, and some rock art being quarried away here as well. And we can see this, perhaps it's a bit small, but we can see these changes here in the planet imagery. A few instances of change were missed in this area. In this case, we have a monastery, a Coptic monastery here, but we have a tree that was cut down and an area of burning, which we observed in the field in February. But this was missed probably partly because there's another tree there in the resolution of the Sentinel pixel. It's still a vegetation containing pixel, so it wasn't sort of generating that strong difference in order to be picked up by the algorithm. So there's a few situations like that where the resolution perhaps is one of the problems. And other situations where we have, for example, graffiti and things like that, they're just not going to be picked up by the satellite imagery. However, I will say a word or two about mitigation before finishing, and the ACAP project and EMENA are working with authorities there to attempt to integrate some of these sites into the sort of tourist circuit of the New Aswan. And here's Dr. Maria Gatto and speaking to engineers at the project here, to sort of have these archaeological areas defined as a really nice way of preserving some of these sites, including that Coptic monastery and some rock art sites here. EMENA is also working with partners and trainees on mitigation, for example, around the site of Cyrene. Dr. Mohamed Abdabba is working on recording and protecting sites here, running his own training courses in the area to sort of highlight instances of change, such as here in the suburbs of Cyrene impacting on cemeteries. You can see this change over time, and just some photos from Mohamed's training, which took place in February, probably one of the last sort of in-person trainings to happen before the pandemic took hold. And there's some more nice photos of this training in progress. Also, some of our partners and trainees have been working on field projects, such as Helen Mecky's GIS and survey project, recording sites in the imagery, but also doing field recording. And this is sort of mitigation we want to see, recording sites and while it's possible to do so. So just to finish up then, so the next steps to explore are hopefully keep being a bit involved with this, but there's more people in EMENA who will continue to work on this. In fact, work is underway right now. So sort of improve the sophistication of the remote sensing techniques we're using, doing a lot more to classify the types of change, not just highlighting that there's change in fact. Trying to bring in more of the historical remote sensing data sets. Once it becomes possible, doing more field validation. And so continuing to support the training course participants to run their own projects relating to this, and sort of coming up with lists of key sites where sort of monitoring and train is just going past, sorry about that, it's gone, where sort of monitoring efforts that are going on. And if you're interested, we've got a recent paper just out on this, including the results of the change detection in Libya and Egypt. So do have a look at that if that's of interest to you. And thanks very much to our funders, ARCADIA, also the Cultural Heritage Protection Fund, which funded the training courses, and to the AMENA directors and the whole AMENA team and partners as well. I think that's it.
Many thanks for that wonderful overview. You managed to get a lot into the 15 minutes left. The format is going to be slightly different in the fact that our three speakers will actually be speaking in turn to give you a walkthrough of the complete workflow that they've been carrying out in South Asia. And so I'd like to introduce Dr. Cameron Petrie. You've already been introduced to, the principal investigator of the MAHSA project. We also have Dr. Adam Green, who's also at the McDonald Institute for Archaeological Research, who's working on one of Cameron's other projects and has developed a lot of the methodology that's been used, that will be used as part of the MAHSA project. And finally, Dr. Hector Orengo, who is at the Catalan Institute of Classical Archaeology. And Hector has been working, again, Hector is one of our project partners and has been developing a lot of the methodologies that will be used as part of the project. So the format, you'll see that Cameron and Hector and Adam will actually talk in short bursts to cover the workflow. So it'll be slightly different this morning, but over to you three. Thank you.
Thank you very much, Rebecca, and thank you very much, everybody. I'm just going to share my screen. We're actually in, of course, 3 different locations. So we're going to be trying to share the same presentation from different places. So can everybody see that, the presentation slide? Can I get one thumb up? That would be good. You can see it?
We can see it. I'd just like to say as well, we are recording now. So anybody who doesn't want to be recorded, please switch off your camera. And if you want to be completely anonymous, please change your name. Thank you.
Okay. So yeah, so while we're doing this presentation, Hector and myself will be sharing and things. So we're just going to try something slightly complicated in terms of the technology, but let's hope it works quite well. So thank you very much for the 3 speakers that we've already had, because I think that actually lays out the groundwork very nicely for the sorts of things that we're going to be speaking about. Now, in some ways, we're talking quite directly about the work that we've been doing in South Asia thus far, but the concepts that we've been working on actually work at a much greater level, and it's also very important to say that we've very much benefited from the existing work that's already been done by the EAMENA project, and the work that's happening from the MAREA project and the Central Asia Archaeological Landscapes project as well. So we very much consider ourselves to be building on a lot of hard work that's already taken place. In terms of the people, there's been a whole set of questions that are actually relevant for the sorts of things that we're talking about. We have worked, I've worked in Pakistan and India. The project remit at the moment is focusing on the geographical area of the Indus River Basin, which is shown in the map on the top right-hand side, but we're also doing the Indus River Basin and neighboring areas. So in some ways, we're trying to focus on a geographical unit rather than I guess, a modern political one, but we realize that it creates all sorts of levels of complexity in terms of who and how we interact with on the ground. But in a sense, in South Asia, as in many parts of the world, there's an enormous amount of potential for the destruction of archaeological heritage. And what's very obvious is that a lot of the damage that's being done today is as a result of agricultural expansion and urban expansion. And so at a fundamental level, what we're interested in is documenting archaeological heritage and hopefully documenting it before it's damaged or lost, and also coming up with methods that will enable us perhaps to identify archaeological heritage before it's damaged, and therefore provide a mechanism, if we can work collaboratively with people, to help monitor things, exactly the sorts of things that Louise was speaking about. And at a fundamental level, the types of things that we're talking about made possible by the power of GIS and the ways that different layers of information can be combined, different specific methods can be combined to give us all sorts of insights. And in doing that, as part of our work, we've built together a sort of, in many ways, a complex workflow but it's an integrated workflow. So we're dealing with existing records of archaeological site locations, which can be combined and cleaned and confirmed in terms of locations of sites. We're going to combine that with landscape analysis using remote sensed imagery, multi-spectral and multi-temporal imagery. We can make use of historical maps, all of which can be combined to identify sites that have been recorded already and sites that have not been recorded, and then combine that with field survey on the ground to ground truth the locations of sites. And in a sense, what's visible on the lower left-hand side is an example of the type of integrated workflow where we combine lots of different aspects together to produce a sort of a holistic view of landscapes and sites. And we can also combine that in a sense to look at archaeological research questions, but also create opportunities for managing heritage generally. Now, the bit that I'm going to speak about is looking at heritage legacy data. Now, if we look at the Indus River Basin and the surrounding regions, we know that there's a large number of archaeological sites that have been documented. And this map just shows you the scale of the landscape that we're talking about if you compare it to a map of Great Britain. If we're thinking about Africa, we're dealing again with an entirely different scale of landscape. So we're dealing with very, very large, extensive areas. And in many ways, we need to use methods that enable us to get somewhere in terms of getting information at a high resolution of detail, but not getting lost in the scale of the area that we're working on. So we know that there's an abundance of archaeological sites that have been identified, but we also know that there are limitations to that knowledge. Now, the traditional method of identifying archaeological sites in South Asia is what's referred to as village-to-village survey, where often archaeological researchers will go visiting specific locations and speak to local people who know the nature of the landscapes around their villages and settlements, and often follow their directions to go and visit archaeological sites. So this is shows you the location of the village of Lohari Rago and a circle around the archaeological site nearby of Lohari Rago. But we also know that there are many problems with the existing archaeological data sets. So there's a big compilation of archaeological sites that relate to the Indus civilization, which was compiled by the late Professor Gregory Purcell, and these dots are shown in orange. In 2008, we did a reconnaissance. This is Professor R.N. Singh and myself and other colleagues visited a selected number of these sites, more or less to identify sites that would be suitable for excavation in an initial sense. But what we discovered was that the vast majority of the site locations were actually incorrect. There are errors in the existing site records. And this creates problems if you're trying to manage sites and also understand the locations and the landscapes. We also discovered that there's often arguments put forward about the relationship between sites and rivers and paleo rivers. And it's very clear that certainly within Punjab, both in India and Pakistan, areas of Punjab, there is not necessarily a close relationship between archaeological sites and river channels. And it was also clear to us that there was our knowledge of archaeological site distribution was heavily influenced by the intensity of the surveys that have been conducted. So of course, areas that have been surveyed intensively have large numbers of sites. Areas that have not been surveyed do not have archaeological sites, but the pattern that we see doesn't actually resemble reality. And what was very clear was that it was obvious that hundreds and hundreds of archaeological sites have been documented, but hundreds have not. And it's very important that we start to come up with ways to systematically document these sort of sites. So I'm going to switch over now to Hector. Now let's see how I go. I'm going to try and unshare it. Hector, do you want to share your screen? And
yeah, I'll give it a try. Let's see how it goes.
If this works well, it works well.
Yeah. Okay, so
there we go.
Let's see if yes. Okay, so I'm assuming you all can see my screen.
Yes.
Okay, so we will start with we will kind of follow a chronological order in the development of our previous two-range project. We started with landscape reconstruction, as Cameron has already said. The location of paleo rivers was really important for us for the analysis of the distribution of sites, but also to analyze climate change. So we, after trying several of the usual techniques for paleo river detection. None of them work very well. Actually, we only detected a few paleo rivers that were quite known in the previous literature. So we had to develop our own methods. You have to take into account this is a very large area with this is more than 90,000 square kilometers, and obviously it's including very different types of landscapes. So we also we had to develop methods involving lots of cloud computing, because no single computer could do this type of analysis. We also, just like Luis, moved to Google Earth Engine. Now we are moving into other stuff, but it was a very good start indeed. So the first way we went about to detect paleo rivers and other paleo landscape features was the Sessional Multi-Temporal Multi-Spectral analysis that was based on the idea that paleo rivers are not always visible. They are only visible during certain seasons under certain environmental conditions. So the first thing we did, we created a new type of index, a normalized difference vegetation seasonality index, that is telling you with this scale from green to brown color which areas have more seasonal variability in terms of vegetation. So then we applied different types of spectral decomposition techniques for the areas in which there was not particularly a lot of seasonal variation, and seasonal multi-temporal vegetation indexes. This allow us to find, I think it was around 70,000 kilometers of paleo rivers. Here you have in the scheme, you can see the main rivers we detected. In green was the seasonal multi-temporal vegetation index, and in red you see the areas where the seasonal variability was lower. The spectral decomposition techniques were very useful. So this is a scheme of how we did this. The vegetation, the seasonal vegetation index allowed us to select automatically which areas should we use the different techniques, and then we apply them and join the results all together. I mean, in this case, we were working with thousands of images from 1984 to 2013, and this is because we choose to employ Landsat 5 because it has a very long span, so we could cover a very long period. So this allowed us to overcome problems like cultivation change, large-scale landscape modification, and get a good idea of general vegetation health over very long periods. And you have here some of the results. In the left, you have the seasonal multi-temporal vegetation index, and on the right, you have the Tessel cap transformation and the PCA analysis. As you can see, these rivers are very visible, many of them. And we were able to trace rivers from the source almost to their end. But this was not enough. We knew there were some rivers we had not been able to detect, and some of the rivers we have been able to detect were not complete. There were areas that you could not draw a continuous line for the whole river. So we moved to a complementary type of analysis. We wanted to do a topographic analysis, but this was very complex. In the previous presentation, Rachel showed you some types of analysis for digital terrain models. Okay, we tried all of those. None of them work because paleo rivers and many other landscape structures, they have very, very slight topographical difference. They are very shallow, but they can be very big at the same time. So we developed this multi-scale relief model to join different cuts of the landscape, several micro-relief analysis, join them all together to create this kind of relief. Okay, so you have a comparison of different techniques here below, and the G is the MSRM we developed. So as you can see, it's the only one which offers a natural representation of the landscape and allows you to detect paleorivers and other structures continuously, independently of how big they are, okay? And okay, this is the result of the previous analysis, and this is the result of the MSRM. Okay, in red you have the positive relief, in blue the negative relief. I'm going to make a zoom in so you can see the differences. Okay, this is a SMTVI, a Sessional Multi-Temporal Vegetation Index. You can see here in dark color the paleorivers that are visible. Those paleorivers actually, what the actual data you are seeing here is vegetation health, seasonal changes in vegetation health for a period of 28 years, okay? And they are darker because those rivers are showing a very particular regime. They get flooded, and they create levees, okay? And levees, the closer part of the levees, they have a coarser sediment. So this coarser sediment results in a lower agricultural production over long periods of time. Okay, so what we are seeing here are actually the levees of rivers that actually grow over the landscape. Okay, and you can see here in the MSRM how these rivers that are visible here actually have positive reliefs, whereas those that have negative relief are not visible in the SM and TVI because they are probably accumulating a much thinner sediment, and you know the agricultural fields on top are much healthy, let's say. So they are very complementary, these two techniques, and together we were able to document almost 30,000 kilometers of paleorivers in the area, and we have a complete paleoriver network at the moment. We have still not published the final results, lack of time, but then we moved to automated site detection. This was also a very complex type of analysis because the area is huge and we are including lots of different environmental settings. I'll show you the workflow we follow. We also employ Earth Engine. We program the algorithm in JavaScript, and we use the computational resources of Google Cloud Platform. We employ Sentinel data, Sentinel-1, which is a synthetic aperture radar, and Sentinel-2, which is optical, multispectral, of course. And then we trained our algorithms using historical maps, archaeoliterature, and also high-resolution imagery. Okay, we use a random forest classifier, and and we validated our data using different methods. This is published. It has been recently published in NAS. So and it's free to access, so anybody can go and check our results, our methods, and also the code is freely available. So it actually only needs to be copied and run in Google Earth Engine. And it's not moving. Okay, perfect. So this is the approach we follow. I'm going to explain it. We use the Sentinel-2 bands, the RGB, the blue, green, red, and then the red edge near infrared, which are very good for vegetation analysis, the shortwave near infrared. And then we also use the Sentinel-1, which is a synthetic aperture radar. It's active. Okay, and it's very good for physical material and has some soil penetration, which in the area we were working was useful in terms of sands. Okay, so we actually the final version had more images, but yeah, we can say we use more than 1,000 synthetic aperture images and more than 3,000 multispectral images. They which effectively constitute big data. Okay, every Sentinel-2 image could be up to 8 gigabytes. So you can imagine the amount of data we are talking here about. And this big data went through some data cleaning to be able to be treated. And then with these composites joining synthetic aperture and multispectral data, we use them to extract our training data, train our machine learning classifier, a random forest. and to apply the classifier. Okay, this is the selection, a small area of with some results. I developed the classifier to be in probability mode. So it's reflected here using this color scale, with yellow being 100%. And 0 being, well, the very dark color. So this is quite easy to see here. And we found more than 500 archaeological sites with very different shapes. I mean, the variability in shapes did not allow us to use deep learning methods. Although deep learning can also perform convolutions in the z-axis between the layers, let's say, these were not consistent enough to use deep learning. So this kind of machine learning approach was very useful. Okay. So from the 511 sites, only 135 were previously known, and it was also very, very cool because we found 4 new very large cities. In the Indus, only 5 large towns were known before. So we have kind of almost doubled the number of large cities known in the Indus. Okay. As with all machine learning methods, we only were able to detect it, the type of sites we actually trained our algorithms with. So atypical sites were not detected because they were not defined in our algorithm. Okay, even though I have to say we had 100% success, we detected all the sites we wanted to, and I think we had 3 false positives, but we cannot know if those are false positive because using validation we could not visit the site. So I imagine at least 2 of those might be sites, but they are just below dune cover. So then with the results, we obviously try to isolate it using thresholding values. I mean, I think we selected more than 70% probability pixels, and then we did a morphologic filter to isolate them, and well, we did several kinds of filter, and then we vectorized them, so we got actual shapes of sites. That was really cool because it allowed us to automatically classify the sites according to size. Okay, and you can see some stats on it. So you have here an image of the distribution of sites. We also use machine learning to analyze this distribution. Okay, you have it here, the image, and this is the irrigated agriculture. So we had very few sites in areas with intensive irrigated agriculture, probably because their multispectral signal was highly distorted. And then we have the distribution of sites in relation with deep dunes. What this is telling us is that probably we have many more sites below these deep dunes. Okay, so this is also very interesting for us to know. So we have a very good detection rate, but it's clear that this is not applicable as it is, this algorithm, this method, to all other environments of the Indus civilization. So we have been working quite a lot lately with improving this method, using also emissivity data from other satellites and new types of active data, and also derived products that I have been developing on purpose to tackle archaeological sites. Okay. With these improvements, we think we can get a kind of global continental scale site detection algorithm. Okay, this algorithm will have a first stage in which it will do an unsupervised classification to divide environmental variability to specific coherent environmental zones. That is, it will not be applying the same classifier to all areas, but it would be divided according to the type, to the environmental character of the area. It will do the same with the training data. Okay, it will classify the training data in coherent groups. Okay, so you will have a specific training data which is coherent and specific areas. Then it will use the results will be filtered, and for this it will also use some kind of segmentation, and then the results of the different areas will be joined. Okay, and you have here, I don't know if it will appear. It doesn't seem to be working. Okay, here now, finally. You have here an example of an area with both irrigated agriculture and drylands, okay? Actually, this algorithm, it allows us to detect thousands of sites, and those are sites. I mean, this is not like previous approaches that were able to detect anthropomorphic soils. Those are actual sites, and those are not modern towns, because our algorithm detects and extracts and takes out actual modern towns. So yeah, we are really, the only problem is that we cannot escalate it now. It cannot be, this algorithm cannot be applied with Google Earth Engine resources because it takes too much memory. But we are now trying to develop our own hardware system to go ahead with this type of analysis. Okay, we are also working on the monitoring on endangered sites. It's a very similar system to the one that Luis presented. Actually, we should talk at some point because we are doing very similar things, and I think our algorithms can be combined effectively. In our case, the algorithm detects the type of affectation. It will tell you if it's agricultural, urban, if the site is in risk of flooding, and we are now developing the looting detection. It will also tell you when it started the site affection, for how long it has been going on, and if it has been interrupted at some point, and how close the agricultural or the urban development is to the site. Okay, you can check it automatically at any moment, although at the moment we only have a 3-day update period. This algorithm will automatically update your project databases if you have them online. Okay, it's not in your own computer. It will need to be your site database would need to be online, and it will update it and give you automatic, the moment you run the algorithm on an everyday or 3-day basis. It will tell you which sites needs monitoring, what is the danger, how close it is. And okay, it's designed to be scalable depending on the availability of investment. Obviously, if you can access a satellite data provider like Planet, or I don't know, there's lots of them, you will have a much closer revisit time, like an everyday, and you will have a much higher resolution that would give you very, very great results. Okay, so it's designed for local heritage management, for people in charge of their own environment, so they can run it and have a good idea of what is going on. Okay, so that was the first part with satellite data, and now I will move to describe our approaches.
We're going to pause there, Hector, I think.
Yeah, thank you, Hector.
We're pausing there, Hector.
We're pausing. Okay, perfect.
We'll have just a brief pause. I think it'd be nice to have a pause. Just we've got time for one question.
You want questions? Okay.
I'd like to invite Sami Ullah to ask your question, please, because it's an interesting one.
Thank you. Hello, can you hear me?
Yeah.
Yes, we can. Do you want to unshare, Hector?
Yes, perhaps.
I was just asking about how can we differentiate between the historical monuments, archaeological sites, and the other settlements present in the area using multispectral images. How can we differentiate? Do we have some specific type of reflectance from these objects?
Sorry, I didn't get the question.
Hector, he asked about the ability to differentiate between modern settlements and ancient settlements. So,
oh yeah, that's an interesting question. Yes, we use the synthetic aperture radar. Modern settlements they have walls, so they have a very high reflectance on the synthetic aperture radar. So the algorithm will automatically detect when there are walls, and would give a very low probability in these cases.
And the archaeological sites that we're looking at, often they've been damaged and destroyed, or some of them are also buried by sand dunes, and the radar can differentiate the spectral signature often from the pottery that's on the surface of the mound, or the damaged site. So it actually throws up a separate signature. But I think the main thing that we need to make sure that we're looking at archaeological sites and not something else is a training data. So we definitely need some confirmation that a specific location is actually an archaeological site. And then we can use the methods to go and find those types of sites in the multispectral imagery.
Great, thank you. So I think we'll move on now to the next section, which is covering the starting with the historical mapping. Thank you, Hector.
Okay, let's see.
I'll do this one, Hector. I start again and then.
Okay, perfect. I'll stop sharing them. Yeah.
Okay. Are we back to showing the maps? So integrated with these the methods that we're using with remote sensing is also one of the complicated legacies of the British Empire was the fact that there was a systematic mapping program that was undertaken in many parts of the world. And as part of the British period control over South Asia, there was the establishment of the Survey of India, which set out to conduct a systematic mapping of the whole of the subcontinent. Now, one of the things that we've recognized in our work is actually something that was initially identified actually as early as the 1950s, was that often the maps that were being created by the Survey of India as a result of the systematic mapping that started in the 19th century and set out to document landscapes. And actually these maps were originally designed to have a military purpose in the terms of working out how to control access across the landscape, where settlement was located, where passes through mountains were located, and all of this had a very specific purpose in terms of documenting landscape. It developed roughly at the same time as the Ordnance Survey in the United Kingdom, which was also carrying out mapping at various scales and various levels. And what happened at the very beginning of the 20th century was that there was a meeting between military officers and the Survey of India in 1905, and the army requested high resolution maps and full color maps of the subcontinent. And so what resulted was the production of maps like the one that you can see on the right-hand side. This is a map that actually shows a part of what was then Northwest Frontier Province in Pakistan. It's actually very, very close to Banu City, which is an area that I worked on as a PhD student. And these maps are at various scales, but the best resolution is 1 inch to 1 mile. And what you can see on the left-hand side is a map that shows the grids that were set up and the map squares, the progression of the publication of these maps over time. And you can see that there were large areas of what are now today in modern Pakistan and India that were mapped at this high resolution. Now, what was discovered by looking at these maps in some detail was the fact that these maps record an enormous range of information, and that range of information also includes the intentional documentation of archaeological heritage, but also the accidental or incidental documentation of archaeological heritage. So you can see at the top, there are a number of features that are marked on these 1 inch to 1 mile maps. We're talking about a landscape that's actually largely very flat. And we're talking about a landscape that often has archaeological sites that are preserved as mounds that exist with some elevation above the ground, but not necessarily a great deal of elevation. And what you can see on the three images across the top are the types of symbols that are used on either on the same map or on different maps to represent specific mounds. Now, these mounds were being documented by the surveyors that were doing the surveying across the landscape. Sometimes they're being marked out as stippled lines, as you can see on the left-hand side. Sometimes they're marked using what's referred to as a form line, which is not a contour, which is the one marked as letter B in the middle at the top. And sometimes they're marked with hatches, which are these little sort of triangular shapes. Each type of iconography represents a slightly different type of mound morphology. But what's clear when we started to conduct the systematic surveys that we've carried out over the last 10 years or so is that there's quite a very good correlation between these features on maps and the locations of archaeological sites. So it's quite interesting. On the lower map, you can see the location of the great Indus civilization city site of Rakhigarhi. Now, this was documented in 1905 as some sort of a village, and it also had a number of associated mounds very close by to it. It wasn't documented as an archaeological site by the surveyors, but it is actually marked on the map. And you can see in the blue circles a sequence of archaeological sites in the close hinterland of Rakhigarhi, which have subsequently been visited, and several of these sites have now been excavated. And it's very clear that these maps were incidentally documenting vast numbers of archaeological sites. Now, sometimes these archaeological sites are extremely visible. This is an example of an archaeological site called Agroha, which is in the Hisar district in Haryana in northwestern India. And you can see on the left-hand side the high levels of preservation of this site. It's not marked as an archaeological site on the map, but it's very, very obviously something unusual in this location. And if you have a look, you can actually see the area where the number 81 is indicated is a high mound, and to the lower right of that is an area with two other numbers, and you can actually see it's a standing walled enclosure, probably a fortified area of an associated area of this settlement. So we have encapsulated on these maps a whole series of information that is not been utilized systematically as a way of understanding archaeological landscapes and the distribution of archaeological heritage. Now, there's various methods that we can use to analyze these maps that provide us with useful insights. So I'm just going to stop my sharing now, and Hector, I'll get you to take up again, and you'll discuss the methods that we've been using for georeferencing and other things. You're on mute at the moment.
Okay, here we are.
You might want to go to presentation mode, Hector.
Yes, I'm trying. It takes some time to actually execute whatever I press.
There you go.
Okay, so it's very noisy, isn't it? Okay, perfect. I'm going to start with the way in which we georeference these maps. Georeferenciation is the first step to actually to be able to extract information with correct geographical location. This is very important for us because we use the extraction of these mounds for the training of algorithms and for survey purposes. So, in this case, in this image, you can see the maps we have collected up to now, but there's still lots of work to finish collecting all the maps of the study area. There are hundreds upon hundreds of them. It covers a very part of South Asia, They are absolutely great because they are previous to landscape modifications of the 20th century. So, you know, with the extension of irrigated agriculture, you need to flatten out the landscape so the water can move freely. Any mound will be the presence of a mound will disturb this water distribution. So many of them were flattened out in this map. Many of them are still standing. But there are also lots of features that could be of interest, okay? However, it was impossible for us to extract data manually from all these maps. It would have taken lots of hours and lots of people because you have to go, I mean, the scale is very big, the 1-to-1 inch mile series. And you know, it takes quite a lot of time, and it's also very difficult to cover the whole area systematically, okay? Because you need to create a grid and go systematically one cell by one cell, and in order not to leave any feature. There are also inconsistencies in the features extracted by different people. Some people would, the bigger sites are pretty evident, but some sites, you know, you might think this line is not that clearly a mound. So depending on how many people are actually extracting the features, you get different results. So we thought the best way to go about was to actually train an algorithm to automatically extract features of archaeological interest from all these maps. But, well, sorry, I think I'm advancing. You have some examples here of different editions of the type of features we are interested. These are mounds, all of them. And yeah, here it is. So this algorithm, we develop an algorithm for the extraction of mounds. As you can see, we also limited the algorithm to 2 hectares because something smaller than 2 hectares tended not to be a site. Okay, so in this way we save lots of work. Actually, you see here the algorithm we were using is RCNN. We have been trying mask RCNN because we are not just interested in detecting site. We want to extract the shape so we can automatically analyze the size, okay? Actually, the algorithm we use for this analysis is UNet architecture, not masker CNN, although now we are moving to masker CNN, okay? So this algorithm provided depending on the type, we develop different detectors. This is a work led by Arnau Garcia, which is I hope he's with us today. Okay, and we also collaborated with Dharam. But well, the results of the algorithms are pretty good. We get from 88 to 96% success. That is, depending on the specific algorithm for the size, you can have from a 12 to a 4% of false positives, and from a 5 to no missed site. Okay, so the results were absolutely excellent. They are going to be, well, the paper is already accepted. It will be published hopefully soon in the Journal of Archaeological Prospection. And we in this paper also we work with French maps, and we try different types of features. For example, we have developed a detector for the word tell, and it works pretty well. We had very little training data, and it had excellent results. I think with a few more training data, we can just map all the word tell in different languages. In all the map series, we are also started to work with Russian maps. So we think this I mean, we want to go for big series of maps because the French colonial series, the British colonial series, and the Russian series cover big areas of the world. And in this way, our detectors can be employed on very, very different situations because they are consistent with the way in which they identify sites. Also, we are working on the development of detectors for specific features like water sources, and okay, we think this has an enormous potential. I have to say though that the thing that we have not managed to automate is the georeferentiation process, which is very complex. And because those are not the deformations on these maps do not follow a mathematical pattern, so you need at least 20 well-distributed ground control points, because if the deviations are too big, then you cannot use this data to automatically compare with the results of the remote sensing, and you cannot use this data to go to the field to actually check the sites. Let's see if it's not moving. See, it kind of hung. Okay, so yeah, that's it. Okay.
Time for a pause again.
Yeah, perfect. Okay, so if there's any question.
Yes, thank you. We have one question from Atta Rahman. So if you are able to unmute yourself and ask your question.
Can you please hear me?
Yes, yes, thank you.
Yes.
Okay, thank you. This is Ataur Rahman from University of Peshawar, Pakistan. It's very interesting presentation regarding the remote sensing application in archaeology. But as a geographer in Pakistan, there is a rapid change in climate scenario, and there is high frequency of hydrometeorological disasters, and there is serious threat to the archaeological sites. I, as a geographer, would like to put a question is, how far it will be useful if joint venture, I mean the multidisciplinary cross-cutting scientists, to work on monitoring impact of climate change and disasters on endangered archaeological sites. Like for example, Harappa is one of the archaeological site which is on serious threat to the waterlogging and salinity problem, which is a human-induced disaster, and they are a serious threat to this particular archaeological site. Similarly, Takhbai is another archaeological site exposed to monsoonal shift, and there is intense rainfall, particularly in that particular region, and due to its location, it is very much endangered situation. So I wish that there should be a joint venture of the geographers who know the hydrometeorological aspects, and they could jointly work with the archaeologists to explore the impact of these disasters and the hydrometeorological disasters on these endangered archaeological sites. It was very interesting presentation by Hector and Cameron. Thank you.
Oh, thank you. Well, I cannot but agree.
Thank you very much, Atar Rahman. I mean, I think that from our side, yeah, I think there's definitely scope for collaboration and interaction on this front. And that's very much why we want to engage with you in like starting with this conversation like today. I think exactly the thing that Louise Rain mentioned earlier and Hector about the monitoring, it is possible to detect change that's occurring at quite a rapid pace. So one of the things, Hector didn't really describe it, but we're conscious that there was actually a very strong winter rainfall season and also a summer rainfall season in the last 12 months. And looking in areas of Cholistan, there was actually a very substantial increase in the amount of land that was being brought under irrigation agriculture. So we can actually detect those sorts of changes where influence of, high levels of rainfall are affecting what administrators and farmers are doing on the ground, and therefore try and do something in terms of raising awareness about that. Because I think the Pakistan and India are such vast countries, it's very difficult to maintain monitoring of everything. But I think using these digital methods, we can actually recognize change. So I think the work that we're describing at the moment, we're very much focusing on an archaeological component, but to understand the archaeology properly, we need to understand the rainfall, the landscape, the hydrology, and all of these things. So it has to be multidisciplinary in terms of getting a good understanding of everything. So I think it's a very good question, and thank you.
Great, thank you. We have one question, another question from Kevin McDonald. If you could ask your question, please.
Hi, hello. I mean, it's great data, and I'm very impressed in the previous lecture about, you know, what can be done in terms of with the TandemX data in terms of beginning to, you know, work out some of these settlement mounds. But I do wonder about some of these detection algorithms, if in a sense they're really time economical, in that, you know, you have missed sites, you have false positives, you know, humans have to check them, and you have a lot of laborious coding to arrive at something that works. In terms of time, if you just started out, I mean, having, you know, many, in fact, 3 or better decades of working with aerial photographs and satellite imagery and doing surveys in West Africa, I can work pretty fast, and someone who's well trained can work pretty fast in finding these sites in terms of doing the remote sensing. Do the algorithms really save you that much time in the end?
Yes.
A one-word answer. I think
it will be, I mean, we are working in terms of, look, I will answer both questions with because you made a previous question, I believe, about the presence of modern towns on top of ancient settlements. If we eliminate these modern towns, we lose the modern settlements. But exactly. we have very high resolution. So I'll try to share the screen and see if I can show you. Yeah.
I guess the other answer to your question, Kevin, is that
at some point someone has to go to the field and see what the features actually are. Someone has to see what's actually there. So our workflows had a major ground truthing component to it right from the beginning. And the idea was to set up a methodology that allowed you to get to sites quickly, see what was on the ground, record things quickly, and digitize everything and have things assessed in a very rapid fashion, but also provide some sort of indication of what the feature actually was, or what the cultural component or chronological component of the material culture you're looking at was actually about. So this is one of the archaeological sites from the surveys that we've done. You can see it's a mound surrounded by agricultural fields. This is actually kind of a rare form for archaeological sites to take in most of Haryana. All right, so this is what I'm talking about. We come in through all these various sources of data that we have. We basically have assembled a database of thousands of potential site locations. Every single one of those white dots is a potential site location. And there's just no way to visit all of those locations. There's no way to record all of those locations off the bat for a single team. So obviously a sampling strategy was needed. So you can see the blue shapes are actually the locations of previous archaeological surveys in Haryana. So you can see the white dots represent mostly historical map features that were pulled from some of the work that Hector described. So you can see that just in this area, which was ostensibly covered by previous surveys in Haryana, there's nearly 10,000 potential site locations. So what we did is we actually devised a strategy for sampling all of the different locations within very specific areas in this region. So if you see those white hexes, that they're falling in between surveyed areas, they're falling in areas that have surveyed. The idea was to treat specific arbitrary geographical grids in exactly the same way. So to have a systematic approach to ground truthing all these various sources of data. So it worked fairly simply. We took the database of previously recorded sites. You can see these 4 boxes here. The database of previously recorded sites. We combined it with remote sensing features. So some of them were extracted in early versions of some of the automated detection algorithms Hector was describing. We also took village to village discoveries. So within each of these hexagonal regional grid units that we visited, we made sure to touch base with several of the villages in the area and systematically record any locations known to people in those areas. And then finally, historical mapping features. All this was fed directly into sort of a GPS capable system where we could actually sort of drive out in the landscape and start ground truthing various features. So the idea was once we arrived, so we put all the data together, export it into a CSV file that goes into a tablet. And on the tablet, we visit each location and assess it. And then we systematically do surface collections on the surface of each site that then feed back to that first location form. All this is done in Open Data Kit, ODK, and is held on a tablet that's then uploaded into the laptop in the field. And that once we collect data from surface collections, systematic surface collections on each site, we actually do rough assessments of the material culture. So we review materials that we collect in a systematic way across each potential site location. And these are separate forms that we use. So we use a master location form, surface collection forms, and assessment forms. And it all feeds back into a database and then goes into the laptop. And you kind of get this cycle that you can use to do the ground truthing. So obviously this is kind of like the ideal sort of site morphology in Haryana. This is just an unoccupied ancient settlement with some agricultural fields to the side. Usually the agricultural fields actually cut in. You can actually see they're starting to cut in here. And most of the time in the field, you actually have this sort of terraced mound feature, which isn't quite so obvious when you visit it on the ground. All right, so upon visiting each site, we mark a central location. So this is the area where you determine whether or not a site is actually present. So in this instance, the site is defined by a number of confirmable antiquities within proximity of each other. And then once you've defined a site, so once you've made a location form, you walk on two transects. We just did simple north, south, east, west transects. Walk either until you encounter something that prevents you from walking, or you get a series of negative surface collections. So at either 50 meter or 100 meter intervals, you can see here, all the material in a 1 meter radius was collected from the surface of the site. And we basically do this, that you get sketch maps in the tablet that we prepared, but then all this is actually fed into a material culture database, real time in the field. So that obviously gives you a much more systematic view of what is on the ground. So this is the site you saw before. You can see there are areas where there's good visibility. There's a lot of material on the surface. So you get large amounts of material culture uncovered. So this is kind of like an obvious site. You can see the steep drop off once you get into the agricultural fields at the side. And then you also have here, you can see this is actually a site location that isn't present in using any of the remote sensing sources that we've experimented with so far. This is what we would call a terraced mound. So this was a mound like this at one point, but it's all actually been cut down. Luckily, there's still material culture evident on the sides of each of these agricultural fields. So using this sort of ground truthing method, that material is still collected, and we still get kind of a database footprint that we can subject to sort of further analysis. So this is a view of the structure of Open Data Kit. So Open Data Kit is basically just a digital form platform designed to record information on the field in a tablet and hold it in case there's no internet connection, so you can upload it into sort of a cloud server. We use a Google Cloud server. And each form has sort of a series of fields. We use the location form, location ID. This feeds back to the surface of data, or to the source of data that it was collected from. So you can see here's our 4 sources of data that we use to identify potential site locations. We visit the locations, record their coordinates, take a photo, record information about any informants, And then you can see all the way here, you get to the determination of whether or not there's actually an archaeological site present. So this means that for all these locations that were reported either on historical maps or through the automated site detection, where there were no sites, we've actually recorded that data, which becomes another source of information we can use to sort of go back and improve the automated detection process. Then you can see we drill down into a series of more specific questions about the site. Then obviously we do these surface collections. So rather than arbitrarily collecting materials on the surface of the site, surface collections are taken systematically along usual transects. So you have the location form at a central location. Then when you do the north, south, east, west transects, and all of these are just marked very simply in the field, in the form. And then once we collect those in the field, all that's bagged and taken back, obviously. So we get to our field camp. This is something some of the field crew, so all the people we've worked with are here in this workshop today. All this material is then counted and then analyzed very in a preliminary fashion and entered into a field database, which we can sort of use to do further assessments. So as a result, you can see in the Two Rains survey area, which is what's depicted here in these hexagonal grids, 264 of the approximately 1,000 locations that were visited actually turned out to be archaeological sites. And we have sort of a rough assessment of some of the features of those sites, whether or not they're intact mounds, terrace mounds, completely flat, irrigated, destroyed. There's all kinds of different categories we use to classify all the various sites we encountered. Okay, so I think at that point I switch it back over to you, Cameron.
Thanks, Adam. If you need to, hang on. Just do that and I will switch over and just finish up. So I guess the important thing to try and say at the end, is that sharing correctly? So the important thing to say at the end is that this, hopefully the workflow that we're describing has a lot of potential in terms of being able to document archaeological heritage sites, but also conduct research and conduct research at one level, but also manage that heritage resource at another level. Now, it's useful to sort of highlight from my perspective that the whole project that we're describing came out of a research project that has been running since 2008. And with the research project had a specific aim of trying to understand the relationship between humans and their environment, and also trying to understand how the relationship between humans and their environment has changed over time. So these are collaborative work between Banaras Hindu University and the University of Cambridge researchers. And as Adam mentioned, there's a range of people that are watching at the moment that have been involved in this work. Now, I'm not going to talk about all the survey results that we've done in detail. I just want to make some quick observations. We've conducted a combination of landscape work, settlement survey distribution, and also excavation. So it's an integrated method, and we're also working with geographers and earth scientists as well. So it does sort of fit with what Atur Rahman was saying before about the opportunities of working cross-disciplinarily. But in a sense, what's interesting for us is that by looking at combining things like Hector talked about, hydrology, landscape reconstruction, we can actually understand the nature of hydrology in river systems, the way those river systems have moved and potentially damaged the locations of archaeological sites, and also the association between sites and hydrological features. Now, I'm just going to quickly show you, these are some time slice images. This is the pre-urban Indus period. You can see there's a distribution of archaeological settlements. Some of them seem to be associated with paleo channels, some of them do not. When we see the appearance of urban settlements, we seem to have the abandonment of settlements in certain locations and the consolidation of sites into particular areas. And there seems to be sites located quite close to the city of Rakhigarhi. After the decline of Indus urbanism, we see a further redistribution of settlement across the landscape, occupation in new areas, different signature landscapes developing in that period in time. And then we have a change in the nature of organization. We move into other chronological periods. Painted grey ware period, we see again a change in the settlement distribution. But what's very interesting is that a lot of the research that's been carried out in the Indus River Basin particularly has focused on the Indus civilization and its associated settlement systems. What's often overlooked or possibly missed is the fact that the majority of archaeological remains in the region actually date to the historic periods. This is the distribution of early historic settlements, which we know about. So these are settlements that date from around 2,500 years ago up to around 1,500 years ago. And then we also know that beyond the early historic settlements, we also have an abundance of medieval sites. So sites that date from around 500 AD up until the more recent periods. And then on top of that, we have modern villages as well, many of which are sitting on top of these medieval or early historic sites. And it is apparent, it's evident in many ways that many of the earliest sites are not being occupied by later occupation, at least as far as we can tell from the surface material. So hopefully what we have is, what we're trying to develop is a transformative way of combining archaeological research with heritage documentation and management. And we wanted to outline to you this integrated workflow that combines a whole number of different sorts of streams. We're really hoping to collaborate with government archaeological authorities, academic institutions, and also especially PhD students, and create opportunities to offer training through workshops, training in GIS methods, training in the remote sensing analysis and site detection approaches that we've described, training in the methods that we're outlining in terms of the historical map use, and also training in the field methods. And we're very keen to, in a way, to collaborate and engage with people with fieldwork, and to empower people to carry out their own fieldwork and ultimately contribute to a centralized repository that can be used by heritage managers and also archaeological researchers in a way of trying to get a much more holistic understanding of the distribution of these archaeological sites and what it ultimately means, but also to try and protect as much of it as we can in the face of sort of increasing agriculture and urban expansion, etc. And I think we've come to the end. Great.
Thank you so much, Cameron, Hector, and Adam, for that fascinating.
University of Arkansas in the USA. So this is sort of a two-part presentation. I'm going to let Jesse recorded a video, and I'm going to let him sort of open it up and talk about the history and some of the unique aspects of the corona imagery. And then I'll follow up with a very short overview of some of the technical aspects of what we've implemented and how you can get access in the future. So with that, I'll introduce Jesse Cassana.
Hey there, my name's Jesse Cassana. I'm a professor of archaeology at Dartmouth College up in New Hampshire, USA, and I've worked for many years with Jack Cawthron on a project we call the Corona Atlas Project. This effort is dedicated to exploring the archaeological and other applications of this really unique form of historic satellite imagery known by its codename Corona. Corona was the world's very first satellite program that was in operation from 1960 to 1972. And over that time produced an enormous archive of more than 800,000 images covering the entire surface of the Earth at relatively high resolution. These images were collected, of course, for military purposes. And at the time when Corona was first developed, there was actually no mechanism for these cameras that were sent up in space to return digital versions of the imagery. And so instead, the Corona camera had a physical film strip in it. It would fill up one of these steel canisters that Dwight Eisenhower is looking at here. They would be ejected from the satellite and parachute to Earth, where they would be intercepted in midair by a plane with a long hook coming out of the back of it, as you can see going on right here. These images, once they were brought back home to the Pentagon and the CIA, would be carefully analyzed. And this program was an enormous success. In the very first Corona mission, the coverage, which is shown in this map, was more than all of the previous spy plane flights combined. And the imagery was of such high resolution that it enabled US intelligence to look for Soviet bomber bases and other kinds of military or tactical issues that they were interested in researching or documenting. But like most intelligence data, after a few months, and certainly after a couple of years, this imagery was really of little more value, and so it was put into cold storage and pretty much forgotten. Until about 1996, when under a presidential order from Bill Clinton, it was declassified. And since that time, archaeologists have been making use of the imagery for a wide range of purposes. Corona is really a unique resource insofar as it's the only source of high resolution global historical imagery. So there are other forms of historical imagery like aerial photographs from national mapping programs that might provide older imagery, but of very small areas. And there are other global forms of historical imagery like SPOT and Landsat going back to the 1970s. But in those cases, the imagery is of such low resolution that you can't actually see archaeological sites and features with much clarity, as in the example of Tel Karkour, a site I used to work at in Syria, shown here in 2-meter corona versus 10-meter SPOT or 30-meter Landsat. We really need this high resolution to be able to see things in archaeology for the most part. And the fact that this imagery is old is really the other thing that makes it extraordinarily valuable. Of course, today you can get high resolution imagery on your phone of anywhere in the world, but this old imagery that is now more than half a century old actually records a picture of the landscape prior to many of the major changes that we've seen in recent decades. So for example, here in the city of Amman, Jordan, as it appeared in 1967, it was relatively small. However, today that city has grown to enormous proportions. And with that urban expansion, the archaeological landscape that surrounded this ancient city has been pretty much demolished. And that is a process we see in many other places in the world. Here, for example, the city of Mosul in northern Iraq, the city of Nineveh, the ancient Assyrian capital, is right next to it, in this case surrounded by this rectilinear city wall. Today, however, much of that region has been covered, including parts of the ancient city, by the expansion of Iraq's second largest city here. Agricultural intensification is another major problem for the archaeological record because even, up until the 1960s in many places in the world, people still used very traditional forms of agriculture. Today, however, they have obliterated that landscape with the imposition of intensified irrigation regimes, deep plowing, and other kinds of strategies that have obscured much of the archaeological record or destroyed many features, as in here in Khuzestan of southwestern Iran. And the third major process that we see, of course, has to do with the construction of dams and reservoirs, which disproportionately impact huge parts of the archaeological record. Here on the upper Euphrates River, for example, in northern Syria, as it appeared in 1968, was filled with thousands of archaeological sites. However, following the construction of the Tap Dam and the subsequent infilling of what's now called Lake Assad, those sites were all flooded and destroyed. Here, a close-up of part of that area in the region of a large archaeological site known as Tel Divi, we can see the Mound and many other sites down in the valley bottom, as well as a series of ancient roadways that once connected with the site. However, today, all of that is, of course, underwater or heavily impacted by the agriculture that was made possible by the construction of this reservoir. And on top of all this, because corona is actually collected in stereo, it's not only possible to view a historic image of these landscapes, but actually to fully reconstruct them in 3 dimensions, as we've done here on that same stretch of the Euphrates River, essentially resurrecting a now flooded and destroyed landscape as it appeared prior to the construction of these dams. So all these examples I've been showing you are basically from the Middle East, where much of my own work has been focused, and where a lot of the research using corona has to date similarly been focused. But corona, as this map illustrates, is really nearly global in coverage and provides all kinds of opportunities for similar work elsewhere in the world. As part of our corona, we have steadily been increasing our coverage out of the Middle East to now include large parts of elsewhere in the world. We have imagery now available for all parts of China, South and Central Asia, bits and pieces of Africa, Eastern Europe, and scattered coverage across much of the United States, Central and South America too. So I want to stop the sharing of that screen now and just move over to take a quick look at the Corona Atlas itself to see in real time some of the things that we can cover. So when you go to the Corona Atlas, this is what you'll see, a sort of general map of the world that shows in red boxes the areas with coverage. I'm going to zoom into a few parts that I think you guys will be more interested in here in Mali, in Sudan, and in Pakistan. With the first example, this shows the site of the city of Timbuktu as it appeared back in 1966, as you can see here on this imagery. We can zoom in and see many of the ancient features of that city that are still visible really well on this imagery. Like those other cities that we saw in the Middle East, though, the urban expansion there has been extraordinary. And with that growth, many of the surrounding landscape has been destroyed. In this case, I'm using the slider tool that we have on the bottom of the Corona Atlas. Another quick example, this shows an area of the Indus River Valley and south of Mohenjo-daro, where today, we're in the 1960s. In this case, let's see what image this is. This is a 1972 image. Large parts of the archaeological landscape are extant. We can see both sites and canals and other kinds of features. Much of this area, however, has been pretty obliterated today with the intensification of agriculture that's made possible the expansion of irrigation canals into this otherwise arid region. So again, this is probably a rich place for the use of Corona. And one last quick example from Sudan. This is the Upper Nile, and in this case, the Merowe Dam, which is right here, and with the reservoir that's formed behind it. The Corona imagery, of course, reveals the landscape as it existed prior to the construction of that dam, where we can see the Nile River itself, along with all kinds of archaeological sites and features along this very rich part of the world. So there are many, many other potential uses and applications for Corona imagery. Hope that you guys will be able to make use of it and will find this resource as fun and enriching to use as I have. Thanks a lot. And I'd be happy to answer any questions by email. Thanks.
All right, so Jesse gave you a good overview there of some of the value and gave you a quick tour of the Atlas itself. But I wanted to talk a little bit about what it takes to get that many images in the Atlas and how we've gone about it. The project has taken on sort of two different time frames of development. The first was when we gathered about 800 images of the Fertile Crescent area in the Middle East to develop the original component of the Atlas. But the last 1,200 images that have been added to there have been done through a variety of different projects, crowdsourced, if you will. And so one of our big efforts to make this available to everyone was to develop a system that would allow you to download imagery, Corona imagery, and to do the same kinds of corrections that we've done to make it available as part of the Atlas. And so Jesse talked a moment about, for a bit, about the structure of the sensor system on the Corona satellites. It was a stereo imaging view, so you had a forward and aft looking video, like camera system like you had here. You can see the film strips at the top, sort of in bows. Those were the canisters. But in order to achieve the kind of resolution that they did over such a large area, and it is quite a large area for each image, the effect on the ground was that you created sort of this bow tie. And so what happened to that is what happens then to a grid. If you had a grid laying on the ground, that imaging geometry warps the features on the ground. And so in order to be able to overlay the Corona imagery on the map at scale across the entire image, we had to apply a panoramic sensor model. And these models are not found in for example, Metashape or Photoscan. So we had to develop our own to do that and apply it. So the first step for anyone who wants to contribute imagery, and there's a large amount of imagery already in the atlas, as Jesse pointed out, but there may not be images over your site. But the first step then would be to go to a USGS, United States Geological Survey site called Earth Explorer, and look under D-Class 1 or D-Class 2 imagery sources, and you can see the coverage here, and you can zoom in, find the images that you like and identify those, and take a quick preview to make sure there's not cloud cover over your area, and download the images from there. But when the images come to you, they come in sort of 4 panels, 4 separate panels. The image you saw, the long strip, is too large to fit on the flatbed scanners that the survey has available. Any scanners in the world, I think, nothing will accommodate that long strip. So we have to piece those together using traditional measures like SIFT or SURF and match those and piece that together. Then in order to rectify these to the ground, we need ground control points measured. Once those are measured, we apply the panoramic camera model that gives you that distorted bow tie view that you see there on the lower left. And then finally, we can project those images onto a digital elevation model of the ground to create the orthorectified views that you have. Now, steps 3 and 4 are really to create 2 different kinds of images, which are both available from the atlas, and we'll talk about that briefly in a moment. So the Corona georeferencing crowdsourcing system is something we've called Sunspot. So sunspot.cast.uark.edu. I haven't given you the link here intentionally because the site is under construction or is being modified. It's been available for some time, but it's being modified to accommodate KH7 and KH9, and so it's not functioning just yet. So we're not ready to give it to you to give access just yet. But Sunspot gives you the ability to implement all of those steps. So the first step here is to upload and process the images, and then sort of define the fiducials or the image boundary on the frame, on the film frame, and then georeference those using Google backdrop imagery, and then be able to monitor the addition of those images and then push them out to the atlas. And so this is the measuring interface that we have on Sunspot. So you have the Google backdrop on the left and the Corona image on the right. And you can see in red there, those are previously measured ground control points. Those are stored in the system. And the new ones that are added, you can see in green there. So this is an interactive system that allows you to go through and measure and remeasure points as you like. Once that's done, you have a list, and we have individual users in the system, so it does require registration. But we have over 2,500 images, I think, now that are in Sunspot and have been corrected to some degree or another. What comes out of that process then are 2 kinds of images. One is a GeoTIFF image that has been orthorectified against SRTM, the Shuttle Radar Topography Mission data from that area. But in order to orthorectify it, we really need a 3D to 2D projection model, and that's what's available in the NITF version. So the advantage of downloading that version from the atlas is that you can apply your own DEM or improve the registration process in an application like QGIS or ArcGIS or ENVI or whatever application you might have. And besides QGIS, there are a couple of other open source tools to do that. So, once that's done and it satisfactorily passes the QA/QC process, quality assessment and quality control process, it can be pushed to the atlas to be available for everyone else. I will note that when you order an image from USGS, if the film has not been scanned, it will cost, I think, $50. It's either a $30 or a $50 fee now. But if it has been already scanned and delivered to someone, it's available free for FTP download. So with that, we wanted to keep it short at the end of the workshop here, but feel free to contact any of us. Jesse and I were the PIs on most of the projects and sort of led it, but Chris Angel at CAST in the USA is the lead developer on this, and he is the one who can answer a lot of specific questions about the mechanics of the site. And of course, we want to thank our funding, and you'll note that the funding has largely expired. We've been managing the site now for almost 4 years and are continually getting small sources of funding to keep it running, and intend to do so for as long as possible. So thanks again for the time, and I'll turn it back over to Stefania.